So what we're going to talk about is how we take power and move it from one spot to the other, and we do that through spinning shafts. So we call this a transmission shaft. Pretty easy concept, so let's take a look at what's going on. So as we think back to our physics classes, that we know that power is going to be what? Power is going to be force times velocity. So in this case, we're looking at our power, and our force that we're going to be looking at, the things that we've been talking about with shafts, is going to be our torque. And then we're going to multiply that by our velocity. Now, in this case, what our velocity is an angular velocity. So how quickly that shaft is spinning around. So those would be the words. So this would look like power is equal to torque times, we're going to continue our classical Greek education. This is lowercase omega. Ooh, that looked awful. Let's redo that. Lowercase omega. And omega is the angular velocity. Now, as we look at this, we have to note one thing is omega, our angular velocity, is going to be in the units of radians per second. I don't know why I divided that by 2. That should be radians per second. And we have to use radians per second to have the units work out correctly. So we can box this because this is one of our equations. Now, typically, we're not using radians per second. A lot of times that we're going to be looking at things like RPM, which is revolutions per minute, or revolutions per second. And so we can convert over our RPMs, our revs per second. Another one you might see is CPS. So this would be cycles per second. Cycles per second, revs per second are the exact same thing. So traditionally, we measure revs per second as what we call a hertz. Named after some guy, I believe he's an electrical person. I actually don't remember. But a hertz is a rev per second or an inverse second. So, since we know this, we can convert between our radians per second and our hertz by saying, okay, well, 2 pi f is equal to omega. Where f is what we call the frequency. I just can't spell today. And the frequency is measured in hertz, or cycles per second, or revs per second. It's all the same thing. So therefore, what you could do is you could take a look at this. And so our normal equation is, okay, well, power is just the torque times the angular velocity. But we can also say that power is equal to 2 pi frequency times the torque. Both these equations are the exact same. So either one of these we can use for calculating out how much power is transmitted on the shaft. So the question is, what about units? Because units are really important. So the units of power are going to be in units of force times length over time. So if we take a look at this in the SI system, we'd be looking at a Newton times a meter per second. This would be the same thing as a joule per second, because a Newton meter is a joule. And a joule per second would be what we call a watt, or just W. So Newton meter per second, joules per second, watt, all of our normal units for the SI system. Now if we look in the British gravitational system, what does that give us? Well, that's going to be a pound force times a foot, or a foot-pound, you'll hear it a lot, per second. Now, with British gravitational system, a lot of times we'll talk about horsepower. A horsepower is not a foot-pound per second. One thing to note is 1 horsepower is going to be 550 foot-pounds per second. This is a good conversion to know because you're going to see it quite a bit as we deal with power transmission in this part of the book, but also you'll see this pop back up in fluid mechanics a lot. Okay, so that is the base definitions of it. Oops. And I guess that's it.